Okay, thanks very much for coming back for the second installment. I'll try to remind us a little bit of what we did last time. The hope is today, hi Wendy, the hope today is that we get into a little more real data rather than made up data. But at the same time, we're taking baby steps, so we're not going to get to where we really want to get in the long run here in 2 lessons. I think, though, that one of the things that we hope to learn is how useful is this to you? Do you think so that you might communicate either directly with us or through AgGateway how you would like to see this go? I think one of my plans anyway is to keep doing things like this at the conferences and maybe also at mid-year, because I think there's no reason to just do it at one or the other. But also keep the record of all of these things on GitHub. So every particular lesson becomes a GitHub, project or something like that that you guys can go to, download, change, and even suggest other things, like please work out this type of example, or it's an open sort of thing. You could communicate through that, just like an open source project. You could add data if you wanted to analyze the data, things like that. So at any rate, last time what we had done was we had gone through the very basics of the data structures of Python. We looked at the fact that in some ways it's very inefficient, and it gets a lot of flexibility out of the language by storing data inefficiently and allowing, really, in some cases, for the computations to be inefficient. And so toward the end of the discussion, we started talking about this package called numerical Python, or NumPy, which is supposed to provide a more efficient interface to store and compute. Okay, so NumPy arrays are much more efficient than these built-in list data types, and they can be computed much more efficiently, which is a very, very important if you're going to apply this as a real programming language or a real computing engine. And we know that, we see a lot of projects out there that are basically based upon Python by the big names in the industry, like Google and such. So at the very first step here, you're going to see me importing the NumPy package, importing another package called sys, matplotlib, and then another matplotlib pyplot package. And we give them all little shorthand names in order to not have to refer to the big name. So I'll go ahead and run this. And then I'll move here to the pandas package. Pandas is built on top of NumPy, and the purpose really is to create this efficient implementation of something called a data frame. Most of you you're very familiar with a data frame. You may not know it under that name, but you know it as a spreadsheet. And so a lot of data analytics and these kinds of things are based upon spreadsheets. This is Python's way, really, of bringing the spreadsheet to the big time. Okay? It mimics also the way that data is handled in R, so it's sort of a bridge to R. There are other objects in the pandas package that are also worthy of looking at, but we're going to gloss over that a little bit. We'll only talk about it when they come up. So I go ahead and import that. And now I'm going to read now is the point where I want to get some actual data here. So in the local directory on this computer, and in the place that you guys will go to get the data, you'll find a file. So dot refers to the current working directory. So I'm running in a particular directory on this computer, a particular folder on the computer. Inside that folder is another subfolder called data. And inside that folder called data is something called case-290-gps-fs10.csv. Okay? So we're going to load that file into the current working directory. And it's essentially an Excel spreadsheet. And we'll look at it here in a minute once we get it loaded. So first of all, we'll print the type of df290. I call it a df because I'm thinking data frame, but in 290 because it comes from something, a case 290, which is a model of a tractor. In this instance, that tractor was pulling a grain cart. Okay, so it says that the class of this particular thing is a pandas data frame. Now, there's several ways to peek at the data. Once it's loaded into memory, the first thing we would do if it was a spreadsheet is we would open the spreadsheet and we would begin to, just look down through the spreadsheet and see what we had. You want to do that here too, but you don't really want to look at the whole spreadsheet at the same time because it may have a whole lot of lines in it. So there's several ways to do that, and I'll give you these commands that just allow you to peek. One of them is called the head command. So if I put df290.head with a parenthesis on it, it will print out the first 5 lines of that. And you see them right there. So the things that are in there are columns labeled GPS time, lat, lon, altitude, speed, bearing, and accuracy. These are things that were logged from a low-cost GPS receiver which was in the combine itself. It was this particular GPS, I believe, was actually logged on a tablet. So the tablet was programmed with a little logger file in it, and these tablets were then stuck to the windows of the machines, and then they operated throughout harvest. There's a few, you'll see there's some hiccups that occur here and there, but there's a little more to it than that. Okay, if say 5 rows wasn't enough for you, maybe you wanted a few more, you can actually change the default number of rows by just putting a 10 in here instead of leaving it to the default. And then it'll print 10 rows out. Okay? And what if you want to look at the other end of the thing? Well, there's a command called tail, which lets you look at the last or the bottom of the file. Sometimes it makes sense. The beginning is junk. You don't trust it. You don't know for sure what's going on. You feel like you got to look deeper into the file. So that's the tail command. It shows me the last lines in that file. So in this particular case, this file had 8,231 lines in it, and they're basically the same sorts of things going on here we see. We do see a couple of weird data points right at the end of this, where it was going 2.5, and then it jumps up to 8. So we're not exactly sure what, you'll see in a second something that probably happened here, but there's some post-processing that the graduate student does that may have caused this, and we'll talk about that a little bit. So it's the first time the major professor happens to look at the darn data. Why not? At least he did it. Anyway, there's one other thing you can do in this version of, I got a lot of guilt problems. I mean, let's have it all right here in front of everybody, and you tape it too, why not? This probably get me out of 10, 15 years of purgatory for sure. Anyway, if I just type df290 instead of tail or head, it actually gives me the first 5 and the end, which is kind of nice. That's nicer than the tail command. I don't know if that works in every implementation of Python, but it works in this particular case. Otherwise, it would try to shell out all 8,000 rows, which would be, actually, if you do it in a terminal, that's probably what it'll do. It's probably something that this Jupyter thing is doing to try to prevent it from blowing up the output here and being unusable. Okay, so we can do a few things here also. We can refer to particular columns by taking the name of the data frame and dot the name of the column. So I can refer to GPS time or .lat or .lon or .altitude as I wish in order to extract from that the single column. Very useful thing to be able to do. So we'll go ahead and run that. And we see when we do run that and just let it print to screen that it does the same sort of thing here. Prints out the first 5 and the last 5 in that file. Now there's another attribute here called the values attribute. So remember that we said that there was a package called NumPy, which was meant to create arrays which were easier to compute fast on. And we also said that this pandas thing was built on top of NumPy, and it was really meant for data science, because the kind of statistician, data scientist way of looking at it is less looking at things like matrices and more looking at things like data frames or spreadsheets. And the reason for that is that sort of the arithmetic or mathematicians or engineers' view of the world is matrices are kind of numbers all of the same kind. So there'd be arrays of values that probably all have the same units, typically. I mean, it's a philosophy more than anything. But in the statistician's world, in the spreadsheet world, the columns can be very, very different things with very different units and so forth. And so it turns out that if we want to convert between them, we need to lose all the column headings and the row headings, and that's what df290.values does. It reduces that matrix that had headings to just a matrix. So I'll run that now. And you see that it does the same thing here. It now has produced a NumPy array of the same values. Now really, that's not particularly useful except if I want to do some special NumPy commands upon it. And there are special methods to compute with NumPy arrays, so then I may need to convert it in order to do that. But because the columns were really different things, you can see a number that's humongous here, e to the 12, and a number that's moderate, e to the 1, that's your latitude, and then you see a longitude number. They aren't commensurate. They don't belong in the same place together. You know, if you applied the usual linear algebra things to these types of matrices would be terribly ill-conditioned typically. So, you know, I'm doing it, but it's not necessarily something you would want to do. You would want to strip out the different columns to do something different with them. Nevertheless, this is one way to translate in between. Now we can check the type. Of course, as I mentioned, it's a NumPy array. So we just check the type of df290.values, and it tells us it's a NumPy array, which is what I had told you before. So it just verifies that. We can also refer to a single row of the data frame by using this sort of knowledge here, or this sort of method. The dot location and 2 refers to the row that's labeled 2. And so if we run that, you'll see that it's produced the row that's labeled 2. It's flipped it up. You know, the row that was labeled 2 was like this with the headings above it. It's flipped it so you can read it like this, up and down. But you have GPS time, lat, lon, altitude, speed, bearing, accuracy, and so on. And it tells you the type of the numbers that are in there. So there's 64, floats 64. And of course, this next command really just says the same thing. It's a pandas series. So that's one of the other data objects that pandas has in it. A series really meant to represent a time domain signal. You know, some function, some phenomenon that varies with time. That's what I would call a series. In MATLAB, we just represent them as just arrays or just vectors, long vectors of numbers. Looks like there's another way to do the same thing. I don't know why yeah. And then I can do the type. I think they produce slightly different things here. Yeah, they did. So one makes a pandas series when I just type df290.loc of 2, but the other one, which types it here, oh, the dot values changes it. The dot values turns things into values, which are really numerical things, numpys. And so it ends up being a NumPy array. So that could be useful one way or the other. I'm not particularly using it here. I'm just kind of explaining it. Let's take a little harder look at the data that we have. Let's take a look at the GPS time. And so this, again, you'll see the type of advisor I am here, because it's like I cannot accept anything my students tell me. And that's why they, poor devils, they get to be part of the family and hang around for a very, very long time, because I've got to look in here and try to understand. So the first thing I do is I look at that GPS timestamp and I say, well, that is a weird number. Let's go back up and look at it up here, wherever the heck I had them. Great big old integers, it looks like, right? Not sure what to make of it. You can observe one thing, though, that's sort of interesting. You observe they increment by 1,000 each time something comes in. So I use then, well, here's one where I run it here, I guess. So there's one of the big integers. And we looked at a few of them again. I'll run it again. I guess I'm repeating myself. Let's go down to here. First of all, each of those entries is a 64-bit integer, which is a lot of bits. The number that you see there is a whole lot less than 64 bits, by the way. So let's note a few things. The GPS timestamps, you're able to read that okay, you guys? The GPS timestamps seem to increase by 1,000 at each step. So now I'm using a little domain knowledge that I have, and probably many of you do. Since most GPS receivers are reporting once per second, 1,000 of these corresponds to 1 second. Therefore, the smallest unit in that GPS time value is a millisecond. Thus, each tick of the GPS clock would then represent, and I'm trying to put this data, I'm trying to make sense of that number because that number doesn't look like July 17th, 2018 to me, and it's bugging me. It's just this big integer. So I'd like to know, is it related to my birthday or anything that I would understand? So each tick of that GPS clock would then represent 1 over 1,000 times 3,600 times 24 times 365 years. Okay, that number, because there's 1,000 ticks to get a second, there's 3,600 seconds in an hour, there's 24 hours in a day, there's 365 days in a year, except for leap years and leap seconds and all the other things they do to this number. We'll ignore all of them. And so at any rate, if that's the case, then this time that we started the log at, which was GPS time 0, okay, that should have actually been 48.5 years before the beginning of that clock. Okay, so now we'll think about, does that, why 48.54 blah, blah, blah years? Is there any sense to that? And so if you need to know that, you call Andrew and Aaron. You Google first, which is what I did. If you Google, the first line I came to was, the world began in 1980. But everyone knows that the world began on January 1st, 1970. I actually can't remember anything. Well, nothing good happened to me before that. A lot of bad crap happened before 1970, but somewhere after 1970 it got better. I think it took like to 1980 or almost 1990, and then it got better. I think it was 20 years of misery. I would never, some people, here we go again. I would never, I don't want to be young again. I would like to be 40. It's a good age. I'd stay 40. Anyway, so the beginning of time was this January 1st, 1970 at 12 a.m., probably in Greenwich, England, or UTC, or something like that. And darned if that wheat harvest data was taken in July of 2018, which is about 48.5 years later. And darned if that number doesn't make sense now. So this is when they decided they're counting those ticks from that moment in order to have a standard count across things. That's extraordinarily useful, of course, now that we know it. Which means really that those timestamps that we get from all kinds of devices can be compared. We know at the same time when things are happening, and that actually in some of the data a little further on here is a useful thing to do. Okay, so while we're at it though, just in case you're worried about Y2K, I think Aaron said it's a 32-bit integer. I don't know. Here in Python, it's represented 64 bits. So somehow if Python was keeping track, we would have to worry about it wrapping in 2 to the 64 ticks, okay, which is, let's see, 1,584 million years from now.
Change it to a 32, though.
Yeah, we could.
Half the machines are out there.
Yeah, we'll do that. Whoop. Oh, did I buy the wrong thing? Huh. Well, that happens like all the time then. Yeah, it can't be right.
Make it 31, maybe 32 wrapped over your
Yeah. Well, it ain't going to make much difference. It's only going to be 2 times bigger. Never mind. We'll come back.
Because 32s are taking them a second to take out your 1,000.
Oh. Righto. Yeah, that makes sense. Okay, well, that's a little quicker.
That's closer.
Yeah, that's 136 years. Still, I'm not worried, but some of you.
As long as they're unsigned.
Yeah, right.
Now they're signed, so you gotta take one of those twos off.
Uh-oh, so it's even closer. All right, Aaron, you got me now. Now I'm worried. All right, so let's go back to the data set that we have. So one of the things I'm interested in that data set is how long did it take to take that data set? Is it a reasonable amount of time for harvesting a field? And I went ahead and I calculated that by taking the max of the GPS timestamps that I found in the file minus the minimum of the GPS timestamps that I found in the field, divided by 1,000 for the milliseconds and 3,600 for the seconds per hour. And I'll get the answer here in hours. And I rounded it because it's quite annoying to see that number of decimal places. And you get 4¼ hours, which is a reasonable amount of time. It's probably an 80-acre field, something like that. All right. Now let's take a look at how GPS time evolves in this cart log file. So I'm going to execute a command here that you see right there, matplotlib command, which creates a plot really of the GPS times as a function of the observation. Now, since it's time, I'm plotting time versus observation. Time should evolve linearly with observation, we would think, right? So we'll go ahead and do that and take a look at what happened here in this file. Okay, a couple weird things. First of all, Python's doing something here which makes it look like there's negative numbers. There's no negative numbers, okay? It takes, what Python is doing here is this is these things times e to the 7 plus this offset. So that is ugly as ugly can be. I mean, I do not appreciate my graphs requiring me to do arithmetic on them. So I'm going to fix that here in a minute. It's not really negative. But more worrisome is these things that are going on. There's these little jumps happening in my time evolution in that log file that I have there. Okay, so what's up with the units on the axis? That's nearly unreadable. We'll fix that. And something obviously is wrong with the log file in this particular case, so we'll take a look at that as well. First, let's fix the odd units and make the plot axes make more sense. So there, instead of plotting the actual df290.gps time, I'm going to do a couple of things here. Looks like I subtract the minimum, so I don't really care when I started. That's time 0. Time 0 is the first point in that file. From the perspective of today's harvest on this field, 0 starts when I do my thing. I get that by subtracting the min, and then I round it here. First of all, I divide to get hours, and then I round it to a certain number of decimal places in order to see something interesting here and get a better plot. And I label the plot, and I label the axes, and I put a grid on the plot. That's what all of these commands here do. So we'll go ahead and run that. All right, now certainly I'm happier with the look of the axes for sure. I see 0 and we run up to, well, 3½ hours, but then something happens there that gets us another nearly an hour. So something's going on. Now this certainly looks better and the axis is readable. I talked about the minimum timestamp. Round was used just to strip off all these superfluous digits. I used 4 because I'm in hours there, and I want my data to not do something weird. In fact, if you make it smaller, you'll see the weird thing that happens here. Because certainly you'd look at this and you'd say, let's just round to 1, right? Let's just round to 1. That's what it's displaying for me anyway. So if I change this and round to 1 and run it, I get all this weird stair-stepping that's going on. So why do you think that is happening? Well, what goes on there is that's rounding in hours. So it's rounding to the 10th of an hour is really what that's doing. Okay, so since the GPS is changing essentially once every second, there's a lot of seconds in a 10th of an hour. 60 seconds in an hour, a 10th of that's 6, right? So there's about 6 in each one of these normally. And so I've artificially added the stair steps here. They're not there. Okay, they're not really there. And since 1 second in an hour's time is 1 over 3,600, I really need more than 1, more than 2, probably more than 3, because 3 is 1 over 1,000, and 1 over 3,600 would actually put a few of them in the same bin, so I better go with 4. And that's why I did that. And then they're not there anymore, but I still have these other jumps that are actually in the log file. Okay? So we'll come back to this. But from the plot, you can see that the logger, well, the thing you can really see is the logger must have turned off at various times because of the jumps. I'm not exactly sure. I think actually the way this logger works, it creates a log file each time it's on and then turns off. And this comes back to basic engineering. We can't keep our loggers running. Well, we actually did we added a feature to our logger which caused this problem, I think. The feature we added to the logger was it would turn on automatically and turn off automatically whenever it lost power. And the reason for that was I didn't want it to log all night. And my nephews, who were running the tractor at Wheat Harvest, would forget to turn it off at night. And so it sits there running all night, and I didn't like it running all night. So we set it up so that it would sense the key if the actual cigarette lighter adapter was keyed, and I think some of them were here, it would sense the power off, and then it would shut down. And so you would hear it, and my helpful graduate student added a voiceover to it. It would go, ending GPS logging. And then in the morning when you started it up, it would go, commencing GPS logging. So what was noticed then by everyone out there running the thing was, on the older tractor, when it got a little jiggly, it'd lose power because it's just in the cigarette lighter. So it was always going, starting GPS logging, ending GPS logging. It was turning on and off as it ran through the field. And then what happened was there's a piece of software he wrote which took all of the myriad log files that the thing would create and condensed them into one CSV file. So then you see them all together, just one appended after the other. But time has passed, and so that's my answer, and I'm sticking to it. And so because of that, we realized that we needed to worry about the power in the darn things. It's always something. That's one thing you can be almost sure of. It might be interesting to see where the tractor was when these events occurred. Maybe it occurs more when it was driving fast, jiggly more, or something like that, but we probably won't learn too much on that. Let's look at the speed. Okay? So the speed in that file varies from 3 to 2.5. They're floats. And so what are the units? Well, are they miles per hour? Are they feet per second? Are they meters per second? Parsecs per day? Okay, it's meters per second, actually, turns out. 2.5 meters per second is about 5.5 miles per hour, which is about the speed that you run the combine through the field. And if you're me, you're even slower because you're just slow. I just thought parsecs was amusing because of this quote, which has always bothered me. Does anyone know why this bothers me? It's the ship that made the Kessel run in less than 12 parsecs. Why am I bothered? Oops. Why am I bothered by that? Aaron, do you know? You don't know? Does anyone know? Well, that implies that a parsec is a unit of time, right? It's not. A parsec is a unit of distance. It's the distance at which the Earth's orbit subtends an angle of 1 second of arc. So if you're far enough away from the Earth that the entire orbit of the Earth looks like 1 second of arc, that's arc, 1/60th of a second, 1/60th of a degree, that is a parsec. Isn't that cool?
What scenario would you use that?
Oh, only in
Only in the movies.
either in the making movies or in astronomy. Yeah, it's certainly a parsec is a much bigger unit of distance.
Far away from the Earth,
If you're that far from home, don't call me because I won't be able to help you. Okay. All right, how do these speeds look over time? So I'm plot. Whoop, there goes my Millennium Falcon again. All right, so we can plot these in just as a plot here. So again, nothing special here. We've used this particular command before. We've just plotted fake data before, but now we're just plotting the time series, really, of the speeds of that case 290. And you see that it gets up to 4. A lot of times it's going this speed roughly in here in the middle, but it varies quite a bit, and it spends a fair bit of time sitting still. We see that as well. And we can also look at the values in the data set by running a histogram command on it. So we see that happening here. And you see the speeds in meters per second that you saw in that log file, which was all operating in the field, by the way. So the student actually does one more thing. After he's appended all of those individual log files into one monster CSV file, he then applies a field boundary filter to it and pulls out individual fields worth of GPS points. So you never see in this the road, except maybe just a skosh of it. Like maybe this tearing out. We just left the field, we're going, and we caught the last 2 points, you know, or something like that. It's something that's going on. At least I rather hope they weren't probably driving that fast. Yeah, maybe rain was coming. Another thing you notice here is a lot of 0 points. So we're sitting still a lot, which is what you would expect a cart to be doing when it's waiting. Now let's take a look at some combine tracks. So in this case, we have another file, this time labeled case 7130, and we run it and we enter it. Take a look here. And we see this is from the same field on the same day, but we see a lot more rows in that file. So apparently, we're on more in the combine. It does not have this jerkiness that's going on. And if we take a look at the plot of lapse time in the 7130, we see that, okay, so this log file looks pretty good. You know, it's incrementing in the way I expect. Looks like the logger was on the whole time, or nearly the whole time. This was not very long, at least, because it looks very, very smooth. The 2 elapsed times are roughly the same, which makes sense because these machines were working in the same field, and so on. Okay. I'm going to look at the speed time series for the case, for the combine, and we see it's a lot more continuous. There is some dead times as well there, but the variability is really small, except for when it goes out on the road potentially here. And the histogram also shows the same kind of thing here. We see some zeros. There's less of them, so this thing is working more than the cart. And it's much more uniform, so it's a tighter distribution there about the times that it's working. Now, if you were going to compute the mean and those sorts of statistics off of this, you would want to figure out a way to cull out this data here that's 0, which is not a hard thing to do. I didn't do it here, but there are a variety of commands, they call them ufuncts, in Python that allow you to do this. You can show, okay, this is just an example. If you, say, wanted to compare these two histograms, you can use matplotlib to make subplots, to put plots side by side. You can also put the same thing on the same axis. So I could have put the histogram for the 290 on top of the histogram for the 7130. Often that's not real helpful with histograms. You need to make them somewhat transparent, and you can do that here too. But if you just lop them right on top of each other, you see very little of use. At any rate, I can see just looking at them side by side that a few observations can be made. Grain carts operate over a larger speed range than combines do. Grain carts look to spend more time sitting. The average speed of grain carts seems to be higher than the average speed of combines when they're working, and that makes sense to us too. Okay, let's look at the scatter plots of the actual points. So now I can take this thing right here and I can run again the plot figure command, but I use as the x-axis and the y-axis the lat and lons from that data frame. So for DF7130.lon, that gives me that column which is longitude, and this gives me the column which is latitude. This makes it plot a dot at each point. And then this makes the color black. And then this just labels things. This forces the axes to be equal. So they'll actually be equal in a degree of latitude and a degree of longitude when I run this. So let's run it and see what happens. And you get a plot that looks like this, okay, which looks, roughly speaking, the way that the things tend to look in the field. What they do in a harvest like this, in fields in Colorado typically, is these aren't planted in rows, it's drilled. And so people go round and round typically to cut the wheat. And sometimes they work out, sometimes they'll leave a corner here and then they work that corner out later. If you look at the cart data, you see that, okay, the activity of the cart is much more random, which, again, you would expect. I hope the cart doesn't go over every spot in the field and trample every blessed thing. He really ought to be just tendering the grain back and forth, and this is the tracks that he did. Now, some stuff is left out. You can see this in the gaps in the data here. So that turning off and turning on stuff that I saw is occurring here in this log file. We don't really believe that it got from this point to this point without touching the ground or anything like that. So again, it points to the trouble we were having with the logger. There's ways of fixing this. I mean, there are various things that you could do in order to do that. I'm not doing it here, but certainly could. Now, one thing you probably know about is you probably know that when you're mapping, when you're plotting things on a map, you really need, well, you need what's called a map projection, right? You've probably seen these things where you show the various different projections show the areas of the Earth in different sizes, apparently, and you know how Texas looks like it's as big as it can be, and Alaska's even bigger. Well, actually, Texas would be smaller. Things north look bigger, right, in the typical projection. So Greenland, I mean, it's no wonder that Greenland was so attractive to our president because it's such a large country. Sorry. Couldn't help myself. Well, anyway, if you're a poor man, so if you're a rich person, then you would go out and you would, or if you had a lot of time, you would go out and find the map projection library, and I would transform these lat and lons to meters in some measuring system. You could do that. Or, and then let me go ahead and go down here, or you could just Google something. So I call it the poor man's map projection. A degree of latitude is about 69 miles everywhere on the Earth. At 40 degrees north latitude, a degree of longitude is about 53 miles. Therefore, at 40 degrees north latitude, that ratio is 69 over 53. Therefore, I can transform between lats and lons by that ratio factor, and I can get better the shape of the field that I'm actually looking at. So if I do that, I apply that factor here by multiplying that, and then I plot it. And of course, it's a pretty small factor, so it doesn't really change too much about how the field looks. And similarly, I can do it for those data points right there. Okay? Now this is the end of part A. What time is it? We have a part B and a part C. How am I doing?
We have 31 minutes.
Oh, good. Let's go to part B. Any questions about this so far?
2038, by the way.
What's that?
That's when the 32 big clocks will roll over, 2038.
2038. Oh, so we really do have something to worry about. I'm just laughing, you know.
The year 2038, probably. I will be retired.
A little bit of flop at the
Yeah.
time. Refreshment break is at 4.
Okay. All right. Well, here's part B. Now we're coming. I did a little bit of messing with this, but I also got this from my graduate student, and this good young man name is Yang Wang, and he's the one that really does the research on machine data. So we'll go through his. It does run, but I'm a little less familiar with it because I didn't change it all yet. All right. It starts out here though. in the same old way. It imports pandas, which is the thing we need to evaluate things first, and because it needs to use this command pd read csv, which is a pandas command. So we'll go ahead and do that, and we're going to get a new set of data. Okay, and I'll show you in a minute that Yang has actually processed this data and applied a map projection to it. So it's already done. And he did it in MATLAB, which I was mad at him for, but he did it anyway. We'll do it, we'll get it running. He did it because it was just easier for him to do it in MATLAB. Most of his work he does in MATLAB, but I'd like to see us do it more in Python because it's, again, for the same reason, it's useful code for people. MATLAB is useful if you have MATLAB, but not so much otherwise. So we look at the top of the file, CS head here, and we see in it GPS time, lats and lawns, and by the way, an 8240 is a combine.
Just to verify, the data has been processed to get it to the CSV?
Yes, this file, well, all that's been processed here is that he took that CSV file that I had in the other ones, or similar one to it, that just had lat and lon and altitude and bearing and speed in it. He dropped bearing here, didn't seem to want them. And he converted the lats and lons to X and Y in a particular or axis. And I forget what the typical one is. UTM. Okay, so that's what you would normally do. Although many mapping softwares, I think, will apply the projection if you just give it the lats and lon point. So you don't really have to do this. But if I were wanting to do some of my own computation on this, then I probably want distance units rather than degree units. And so for that reason, he's done this. In fact, we do want to do distance calculations here because one of the things we want to do is, and we'll do it here in this file, is we want to compare the distance between the cart and the combine. And the reason we want to do that, why do you think we want to do that? Well, I guess to know whether, what's that? Yeah, well, I want to know when it was unloading on the cart. So I have a proxy here for unloading events, as in a, yes, it's too far to be unloading on the go. So we're doing a very simple thing here, but we'll talk a little bit about a more complicated thing you could do. But all we're doing here is comparing the distances. And most of the time, the distance between the combine and the cart is pretty large. Actually, we'll go ahead and do that. So C is for combine, K is for cart. He'll now load in the cart data, and then he'll look at the top of the cart data. And then he's going to look here at the GPS times involved in the cart set. And then he wants to, okay, so at this point here, he's doing a particular thing here, which uses the fact that GPS time is that unique thing. Okay, so the GPS, even though these machines were logging time separately, when they have a GPS timestamp, that GPS timestamp can be compared across the two machines, independently gathering data. And of course, if you can imagine, it synchronizes the log files. And so now I can join them. I could say at this time, combine was here, cart was here, and they're there at the same time. Otherwise, I got to keep track of time as well, right? Because merely being at the same place does not mean you crashed. You have to be at the same place at the same time. Okay, anyway, so what he does here is he uses a pandas command which merges these two data frames, C and K. It merges them on the GPS time value, and it picks the ones where they agree. Okay, if anybody's an outlier, if there's no GPS time corresponding to one or the other, just leaves those out. And you would want to check that to see how many you lost in that way, but for now we're not going to worry about it. Okay, so it does that merge, and then I'll show you the new thing here. So now you see a bigger table. It's got the same GPS times because they were in the same files, right? It's got a latitude for one and a longitude for the other, and X, and the two values in meters. It calls them X underscore X and Y underscore X. I don't particularly like the use of I would have had a more descriptive name than that perhaps, but nevertheless, it's okay. And then the Y. Okay, so one is for C and one is for K. It would have been better to call them C and K or something like that. And the speeds that are there. Actually, that's an interesting thing. I don't know how he joins the speeds, because there's only one speed. I'll have to ask him that. Oh, it does. Yeah, it doesn't join the speeds then. Very good. So then this file actually has everything I need really to know what's going on in the interaction between the cart and the combine. We don't necessarily use it here, but let me go ahead now and show you the next thing, and then we'll come back and I'll say what we probably should have done, which would have been a little more complete than what was done here. He did it in his MATLAB code, he just didn't do it here. So now he's going to import numpy as MP in order to do computations on this array. And the first thing we're going to compute is the distance between the cart and the combine. So that's the usual distance measure, the square root of the difference between x squared plus the difference between the y components squared, right? So that computation may not look like it there to you, but it takes the x component of ck for the cart minus the 1 for the combine, and similarly for the y components. And so this gives us the x and y values of the differences at each point in that thing. And then it turns it into a distance. It gives you x and y, and it gives you the radius or the hypotenuse. So that's what dp np dot square root does. So we'll go ahead and compute that. And now we have a new pandas series. And this represents the distances in meters between the combine and the cart as it executed their functions in that field that day. We can compute the minimum in distances that we saw, and we found that to be 5.4 meters. We can compute the maximum in distances that we saw, and we found that to be 816 meters. And then we can compute things like the mean, and we see, oh, most of the time they're far apart, which is kind of what you would expect. Now we'll go ahead now and plot some things here. Okay, this is the distances again. And now we're going to plot the distances using Young's way of doing it. And you see it's taking a little while there. You saw when I clicked go and the thing went to a little star, that means it's computing. So you can see there's some time involved in this. I'm betting you that this could be sped up. Anyway, let's take a look here at the distances that happen in that file. So most of the time they're quite far apart. We can identify, though, looking at this quite easily where the unloading events occur, because these happen when the combine and the cart get close. So if I put a little threshold on here, like 5 meters or 7 meters or something like that, and just clipped it across the top here, everywhere I got a nice dip, I probably am unloading, especially if that dip lasts a little while. Now, you look at some of these that are really short, like this one right here. That might not be an unloading event. That might be the combine and the cart got close, but they just kept going, right? So there is a time involved in it that you would expect, right? So another thing we could do to make this more accurate would be you could look at the heading. You could look at the speed. In order for a combine and a cart to be unloading on the go, they need to be roughly matched in speed. So you could probably discern more accurately the exact moment that it began to unload based upon where it was. You could apply some other filters. At least in my experience, the auger's on the left of a combine. The auger on the cart's also on the left. So a combine has to be to the left, or to the right, sorry, of a cart if it's unloading on it. And so if it's on the other side of it, it's probably not unloading, unless some dumb butt, and I did this once, tries to unload on the wrong side, thinking that would be cool. And you know what it was? It was all night fixing that auger on that combine. Yeah, that was that one I talked about, my favorite combine ever. That's one. Okay, you know, sometimes when you do bad things with a combine, you become good friends. Anyway, that's the end of this one. Now we'll go to part C, okay? Okay, so part C is even more complicated. Less explanations, more complicated. So now if you come up here and you look at what we're doing here, we're actually going to read in, and I don't know why we're reading this. I'm going to go ahead and just run this one because Young doesn't use it. The first file he doesn't use. Let me just run it to make sure that I've imported everything. And you can see how long this is taking, by the way. And then go down here. Well, what the heck, I might as well look. It reads something called a log file. Okay, so it's basic. It's not a CSV file. It could have been a CSV file. For some reason it's known only to Young. Its delimiter is a space. Okay, and when he read this file, he read out the columns, or he wanted to read in the columns named TS, PGN, SRC, destination, PR, and payload. So what those stand for, this refers to the ISO 11783 or the CAN standard. Because this log came from the ISO blue that was attached to the, actually is this one, this is the combine. Yeah, so the 7130 combine. It came from a logger device of our own design that was attached to the CAN bus. The things that, and it's been processed to get it into this form a little bit, a fair little bit actually. So you see some things that are going on here. There's timestamps. There are things called, I think they're called parameter group numbers, PGNs. There are sources and destinations. These refer to addresses of the objects that are talking on the CAN bus. So the tractor or the combine has little computers essentially that are attached to this network. It's an actual wired data bus, you know, akin really to Ethernet, but perhaps older fashioned, or maybe that's not a fair thing to say. It's really for machines, automobiles. Bosch, I think, it was behind the standard originally. And then it was adopted for heavy trucks, and it was adopted for agricultural vehicles. So all these devices like Climate's Puck and John Deere's devices that would attach to these kinds of things, they would read this bus. Okay, and so source refers to the source address of the object that's talking on the bus, and destination refers to the thing it's trying to talk to. Okay, so you can learn something from the source and the destination, and you can learn something from the priority. The priority says, how important is this message? And then the other thing is the PGN. The PGN tells you what the message is. Now, some of the PGNs are public. And they're public in the sense that if you have the standard, I think sometimes you have to buy that standard, but if you have that standard, then you know those things. And of course, there's no, in those particular public messages, there's no proprietariness to them. I don't really know why people pay for the standard. Universities tend to have that standard, so we have access to those messages automatically. But then there are other PGNs that are proprietary information or proprietary to the companies involved. So John Deere has theirs, and Case New Holland has theirs. And they don't tell you what those PGNs are, except for some of them that are public. So some of the ones you really want in an agronomy setting is you want the mass flow reading off the mass flow sensor. Well, that's one of the secret messages, dang it. And there's a few others of that moisture message, things like that are there. So when you get the PGN, it tells you a couple of things. It tells you what type of message I am. You know, this data that's coming following me, and there's a frame set up here of, you know, header, PGN, source, destination, priority. These are bits described in a word, a really long word. And then there's a payload, and you see the payload over here. The PGN tells you what is talking or what this information is. There's a PGN for yield. If you know the PGN for yield, you can decode it and you can make a yield map. Okay? But you also have to know, and the PGN also tells you this, or the standard tells you this, the secret part of it is, what bits over here in this monster payload correspond to the reading. And what is the unit and translation between them and a number you would understand, like bushels or pounds or something like that. So there's some decoding needed in order to work with this thing. And I'm going to go through how. So first of all, Young decided he only wanted the timestamp, the PGN, and the payload. He's not going to look at the source or destination of priority in this case. So for some reason, instead of just filtering that out, he decides to execute the read again. So I will do that because that's what he did. And now it sits here and it does this. Okay? And then we show the beginning part of that file. Now just with timestamp, PGN, and payload. Okay? And look how big it is. So there's a lot of messages in this file. You're getting to the point of a place where a spreadsheet wouldn't be happy with you anymore. So that's, I guess, is that the boundary of the known universe of big data and data? You know, something that Python is happy enough to handle, but Excel would not. So I don't know, how big will Excel handle? There's 7 million rows in this, so I don't know. Okay, so this is 10 times bigger than what Excel wants, you know. So that's so here's a spot where this tool is now suddenly in the realm of the useful to people. Okay, we want to only get the engine load messages. Okay? And we know that the engine load PGN is 61443. And there's nothing wrong with knowing that. You're not a bad person to know that. It's okay to know that. That number is okay. So we do that and we filter that thing by that PGN to produce something. And I don't, it's kind of ugly what he did. He's got these integers here. Let's run it again. Oh, what this shows you, well, okay, so what it does is it goes to this file. I don't know if I'll find a 61443 in it. I got something close, 61444. There it is. There's the first one at the very end. So what it does is it goes into this file and it pulls out every row that has that PGN in it. Okay, and so that's what comes out of here as an array. Now we're going to only take out the rows with the indices we found. Oh, okay, here you go. Here's what it looks like. So the 27th in that original guy happened to match that PGN. Then the 57th did. Then the 106th, then the 175th, and then on and on and on throughout it. Young does not like that the indices start at 27. He wants them to start at 0. So he's going to remove that here and reindex that thing so it starts at 0. That's what this command will do. Okay, now we're happier, I guess. And we have gotten rid of a lot of messages. We've now got, it looks like, 198,380 left that matched that PGN. So out of, what was it, 7 million or something like that, we're down to quite a bit less, actually. So engine message PGNs are frequent, but they're not, they're not by any means hogging all the time on that bus. Okay, now you look and you see, this is how people actually go about decoding these things. Am I running out of time? Oh, okay. I'll speed up. You can see the message, all right? You don't really need any more to see the message. You can see that the only thing changing here is these bytes right in the middle, 40, 41, 40, 2F, and so on. And so this is, when you wonder how do people reverse engineer this kind of thing, this is basically how they do it. But you don't need to reverse engineer this. Okay, now we want to create another column. So we're going to process this a little bit, filter out just those bytes, because they're the information bytes, about engine load. Engine load ought to be a percentage of full load. So let me run this. And we can see here now we've pulled out the engine load hex bit. So in this standard, there's a lot of superfluous information all set to 1s. Those are set to Fs. F in hex is all 1s. Now we're going to convert the hex value to a decimal value. He uses this command here to do this, but it's nothing more than the fact that you take the numbers are 0 to 15. 15 is F, and then it's base 16. So if you go into the first units, you have a 16 for a 1, 2 times 16 for a 2. So it's, you remember middle school when they made my kids do it. You know, convert number systems and that kind of thing. Anyway, you could do it. I'm sure you could. Or you could use this command that does it here. And so we'll do that. And now it's got the engine load as a percentage. So 40 hex is 64% engine load on this machine. Okay, now he's going to do a couple other things. If you noticed at the very beginning, we didn't have any GPS in that file. Again, I'm a little not sure why that is, because the logger is supposed to be logging GPS. But as it turned out, I mean, the IsoBlue has a GPS connected to it, so it has its own source of GPS, and GPS is sometimes on the IsoBus, so it's multiple ways of getting it. However, there was also a logger in there. There was one of Jagwang's loggers in there, doing the old-fashioned logging. So Yang is going to join those 2 GPS files in order to put GPS back in his log. So I guess it's good to have multiple ways of succeeding in the world. I just wish we didn't have to use them so often. Now it's running here and doing this. It's basically figuring out a way, and this I'm not going to, it's figuring out how to put these 2 files together. And there's one major thing that he talks about here, and I'm going to gloss over it a little bit because we're out of time. But the messages on the IsoBus are coming much faster than once per second. GPS messages are coming once per second. So what I want to do is I want to take a value from the IsoBus, like engine load, and attribute it to a position in space. So I can make a map of where was the combine working hard and where was it not working hard. This might tell me something useful, right? I have to downsample it though, because I got a lot of engine load messages and only a few GPS points. So there's various ways you could do that. You could find the messages that are closest to the GPS point and average them and then assign that value to the GPS point. Or you could just take the closest one. Or if, in the case here of timestamps that actually agree, you can find the one timestamp that goes with that thing and put it on there. And so I think that's what Yang is doing here. He runs this thing to do this, and then he checks to make sure he's got the right number of points so that it all worked out. He had 99.15. He checks to make sure he does. He's still got 99.15. This is good. He's doing this in order to create a map, so I'm going to go through that. Okay, let's see here. Oh, actually, now we're reading the GPS. Something else was going on there. Never mind. Here's the GPS, and now he's modifying it a little bit to make it agree with the right timestamp here. Okay. Then he's going to merge again the two frames together using that PD merge command that we had done before. Okay. And now finally, and this is the coup de grace of the whole thing, the final moment. Hooray! He's going to map it with a map projection and a token to this thing called Mapbox that allows you to access their maps. Okay? So let's run that. And it'll take a little while. There it is. So this creates a map of engine load in that field. And let me zoom out a little bit here. And you can see where we are in the world. I want to see. Well, okay. Grant, that's in Nebraska. Chapel's in Nebraska. Ogallala is Nebraska. That's McConaughey. That's the biggest puddle of water in Nebraska. Not that it's that big, but you know, if you ever fly to Denver and you see a lake, it's probably that one. Okay? Especially if you fly from Chicago. You tend to fly over it. And I live, or my people live about here. This is Holyoke. Amherst is right around here. Venango's there. That's the 16-mile corner. That's the things that, you know, you grow up with. And this is the little blob of points that represents that field and the engine load on that combine as it was doing its thing. And so you can zoom in and you can see what they were doing. And there they are. Okay, so the percentages are mapped by this color bar, and as this thing worked this field, you see this going on. Now, a couple of things are going on in here that if you're a astute observer of tracks of machines, you might say, that's a hell of a big header on that combine, right? They're only making like 6 passes or something like that, and he's worked in 80. It's not that big. There's 2 combines in that field. This one is the bigger one, but there's 2 combines in that field, so it's only showing you part of it. Okay, you could easily join the 2 and create a map of the 2 joined together. You'll also notice another thing that's going on here. Because this combine got a lot bigger, it's got a bigger header on it, we can't turn the normal inside corner, we flatten the wheat. So now we kind of waste a little, it used to be that inside corner was very fast. And then you would come later and you would leave just a little snippet of wheat and you'd come back and cut that. Now you flatten it, nobody wants to do that, and so they create an outside corner and come out of the field and go back in. And that's it. Are there any questions about all of this? Okay, that's fine. One thing to think about would be if you're really, if you're really wanting to do these things, which I would encourage people to do. I think it's a wonderful thing to sort of think like this and to think computer-like. And Python's a good language to do it in. You don't have to become. You can do useful things in it reasonably quickly, and you're not necessarily saying, oh, I'm going to become a computer whiz here. You want to just have a tool that can handle some things that Excel can't handle. It's one of our goals, actually, to build some tools that are sort of like Turbo Excel. Now, of course, as soon as we build good tools, Microsoft will come along, beat you or something like that. But there's a role, sort of, I think, in sort of joining the kind of classical spreadsheet tools with these sorts of things by creating little projects. But moreover, I think in terms of an educational thing, how should we run it? My feeling is you guys, if you're wanting to learn it, you really need to go in there and get this code and run it. And you can do that. I will put it in my GitHub and you can go and get it. And what we could do if we wanted to make a series of these things that would happen, say, at every meeting, we could just add to it. Let's do something more. We'll start from this point and we calculate where the unloading events are. And we actually have the truckload data that came off of this field. So we could actually try to attribute the truckload into the field. We could keep track of where we were combining when that cart was filled, when that truck was filled, and create a probabilistic, not a perfect, but a probabilistic yield map, And you could do other things with it that would be interesting, because when you go into the elevator and you take your load, you get graded. Combine doesn't grade it for me. They do. They tell me my dock, they tell me my protein, they tell me these things. So you could conceivably create a map of noxious weeds, which is a big problem in this area. Jointed goat grass is when, if you farm right, you don't have it. But if you're buying land and you're expanding your farm, it's often a problem. You get a lease on a big piece of ground, and the reason you got the lease is because the guy that had it couldn't make any money because it's infested with noxious weeds and things like that. And so you got 2 or 3 years worth of work on that. But you could create maps of where those are in this way.
So the reason you're doing this Python is it's more readily accessible to a lot of people. At some point in time, this data, where does it go to an analytical tool as well, right? I mean, I'm sitting there watching every step that you're going through here, and
What do you mean by an analytical tool, I guess?
Tableau or something of some nature. I'm looking at all your data points, all the other pieces that are going on here, and I'm sitting there building. I'm like, yes, I want to see those points, and I would zoom in, and every one of those clickable points, I can click it, get into the details, zoom in, zoom out on the other pieces here too. These are all great checkpoints to see where this stuff is.
Yep.
Your combinations on the GPS point. That's
Well-
where the curiosity gets to, and then you're dealing with how much data as well. This is all. At some point in time, you got to aggregate it up a little bit to get the
Oh, yeah.
flow.
No. In fact, we have,
80-acre field.
this is an 80-acre field, but we have for 4 years worth of data like this from 5,000 acres. So it's not nothing, but it ain't really big. It's big for us, but it's not big for the world. But it's not meant necessarily to solve the problems of wheat production for Colorado or Kansas, but it's meant to show perhaps how you might start to do that. And then because we are researchers, so ultimately, I probably won't go to Tableau. Number one, I've never used it. So most likely, I'm going to do visualizations that I can do in Python, in part because I'm trying to train students in how to really code. I could see someone who was working with us in this same GitHub repo going to Tableau and developing things there, but it probably wouldn't be us. I don't know. Have you guys any thoughts on that? Yeah, I mean, yeah, I don't want to dismiss it. It's just, what's that?
Power BI is free unless you want to upscale it.
Yeah. We would probably focus more on free things for a variety of reasons, just because we're going to try to turn things loose free. And then the idea would be that if you saw something or you piddled with something and you saw something, oh, we need to do that, and then you want to make it enterprise, then you're going to have to go to these other services. But it probably wouldn't be us doing it, but we'd be more than happy to consult on it with you or to learn about it, you know.
Well, and that's the part where I think when we're looking at the raw data, and everybody uses this whole term of IoT, how that is, it is just a bunch of data in a different format that people are just used to seeing in something that's rolled up into a Excel file that makes sense. And then
Yeah.
But you were talking tons of data, and it is in how you look at the explanation of some of the
Yeah.
columns you're showing there. You understand what's behind it, but Joe Blow might not. And
Right.
as you become more familiar with it. So it's going to allow you to get to those next levels, but you got to get into the weeds here first.
Yeah.
Details.
Yeah. Any other questions? Anyway, please do reach out to Wendy and let us know how we could make it better, and if it's worthy of spending the time on. It's not, you know, they have to decide how to spend the time of, you know, they're renting this room and whether this is a good way to spend their money. We're happy to provide this service, and we think it's a good role for us because, you know, we're not in the business of producing a product. It's just not, it's very bad when the university starts to think they are. Sometimes they do. So we're pretty clear on it. You know, so we do seek things that are kind of in our wheelhouse, and you can help us by saying, well, we kind of understand your wheelhouse. You're a professor, you profess, that's what you do. Teach us more about this or experiment with that. Or if this GitHub thing took off and people wanted to throw data sets at it for people to play with, data sets that were harmless, you know, I mean, you're not going to give your key core stuff, but something that illustrates something you're curious about, maybe people would start to play with it and it becomes kind of a community hacking portal or something. Anyway, I will end here, and I thank Wendy and AgGateway very much for letting us have these 4 sessions to profess at you. Thanks. I thought they went pretty well. Andrew gave one yesterday after me, and a lot of people liked that too. It was
I got some good feedback.
good.
Yeah.
I mean, we thought of